In today's lecture, we will continue our discussion on integer programming formulations. In the last lecture, we formulated the grouping problem as an integer programming problem. Today, we will begin with something called the fixed charge problem, which is related to the grouping problem, but slightly different. Now, the problem is like this. Like, suppose there are say 3 or 4 locations where somebody would like to establish a factory or a warehouse or a distribution center or something like that. So, these will be the central nodal points, and from this factory or distribution center we have to send items to different places. So, these will be the customer points which will be there, and so on. Now, there is already an established connectivity, saying for example, this point is connected to this point is connected here, this point is connected here, this point is also connected to this, connected here and so on. So, you have a certain connectivity associated. You have to make sure that every point is connected to at least one of these or more than one of these and so on. Now, each of these, for example, we will call these as I, these are the i's and these are the j's. So, we will say that there is a requirement of dj for each of these j's, and there is a capacity ai, we will look at that a little later. There is a transportation cost Cij of transporting it from I to j. There could be an ai, which is a capacity restriction also. Now, the most important thing is that it is not that you have these plants located in all these 4 places. What you want to do is, let us say you want to locate p number of plants, say p could be 2. So, you want to locate, let us assume that these are candidate locations for plants and these are the demand points, and there is transportation from the plants or the factories to the demand points. Now, there are 4 candidate points, but we want to locate it only in 2 places, not on all the 4. And then there is a fixed charge Fi of locating something in location I, that is also there. Okay? So, in order to create a facility, I have a fixed expenditure which is called a fixed charge. That is why this problem is called fixed charge problem. So, the variables will look like this. You can have yi equal to 1 if location I is chosen, and xij is the quantity transported from I to j. So, your objective function for this problem will be to minimize sigma Fi yi plus sigma Cij xij. Now, right here you may say that it will come much later, of course. You may say, for example, if there is an absolute connectivity, every one of the j's is connected to all the i's and so on, a complete connectivity between I and j, then you may formulate this problem for a fixed number. For example, you may say sigma yi equal to p implies that I want my factories to be located exactly in p out of the m possible locations. You could have that. At the same time, if you do not have this complete connectivity, what you would like to do is to have a minimum number of locations. So, you will ignore this constraint and let the problem decide the number of yi's that it wants to have. So, you may have this constraint, you may not have this constraint, depending on the situation. You may also have an xij less than or equal to uij, which is the link. For example, this will be uij, which is the capacity connected with the arc ij. I may be able to transport a maximum of uij between I and j. If you do that, then it is called a capacitated problem. If you leave out the capacity restriction, it becomes an uncapacitated problem. For example, the standard transportation problem that you have formulated is an uncapacitated problem. It does not put any restriction on the limit on xij, and all capacity constraints or capacitated problems have constraints which are upper bound to that xij. So, you may have a capacitated problem, you may have an uncapacitated problem. If you have a capacitated problem, then you will get this constraint. If it is uncapacitated, you will not limit the xij's, it can be anything. Now, sigma xij should be less than or equal to ai yi. If location I is chosen, which means yi equal to 1, only then the ai capacity is available for you to be distributed, otherwise it is not. A standard transportation constraint would not have this yi, it will simply be sigma xij less than or equal to ai, j equal to 1 to n, of course. Now, because of the location decision that comes along with the transportation decision, you will have sigma ai yi, right. Is that clear? Okay. If you do not have this capacity constraint ai, and if you assume that the plant can produce an infinite number or whatever is needed, then this will look like sigma xij is less than or equal to m into yi, big M into yi, where big M is large and positive and tends to infinity. So, when the location is chosen, it can produce a maximum of big M. If it is not chosen, it can produce only 0, so nothing can come out of it. Sigma xij greater than or equal to bj, because what is needed in destination j should be met. Now, all this will work very nicely if there is complete connectivity among the i's and j's. Otherwise, what you can do is you can leave out those xij's for which there is no connectivity, that is one, or you can set that uij equal to 0, so that the whole thing does not exist, you can do that, or you can even go back and put another aij, which is like an incidence, which models an incidence, aij equal to 1 if there is a link between I and j. You can do that also and suitably bring that aij or bij. If it is going to confuse with ab, call it some c, not c is also used, so some etc., some number, some rij or whatever as an incidence between I and j, and use it suitably. So, xij will be enabled only when that rij is 1, otherwise it will not be enabled. You can do it that way. Easiest thing to do is put all the uij's to 0 where you do not have the link, that is the easiest thing to do, and so on. So, xij greater than or equal to 0, what is? bj is a requirement. Where is the dj? Oh, I am sorry, so I should be consistent, so call this as dj. So, yj or yi equal to 0, 1. So, this is called a fixed charge problem. Now, this is a very important problem in location, allocation, distribution, supply chain, and in all those areas particularly when you are looking at decisions at multiple levels. For example, you could have factories, you could have distribution centers, you could have warehouses, and then retailers. So, the problem will look like I would want to make say P1 out of M1 factories, P2 out of M2 distribution centers, P3 out of M3 warehouses, P4 out of M4 is the ultimate customer, so you will not have that. Then you will get a series of fixed charge and it becomes a fairly complicated problem. Okay, but this is the reasonably similar to the grouping problem, but it has additional constraints and restrictions. We look at some more examples of integer programming formulations. We will also take the travelling salesman problem as the next example. So, to begin with, let us take a 5-city travelling salesman problem where the distance matrix is given. We can generalize it to a n city, there is no problem at all, except that we need to consider the case where n is odd and n is even separately. We will right now take 5 city where n is odd, and we will assume that we have the distance matrix that is given to us. So, dij is known, distance dij is known. We can assume that it is symmetric, but it is not absolutely necessary that it is symmetric in a travelling salesman problem. Normally, distance between I and itself, any point and itself is 0, but it is customary to define dii as infinity in all travelling salesman problems. So, we will put a dash here in all these 5 places indicating that it is infinity. We will see why we do that very soon. In all travelling salesman problems, you can almost close your eyes and put infinity along the diagonal. You will never have a 0 in the diagonal. Now, let us define xij equal to 1 if the salesman visits j immediately after I. Now, there is one more aspect which we will touch upon. Unless otherwise stated explicitly, it is assumed that the travelling salesman distance matrix for any TSP will have to be square because it is a distance among a certain number of cities. It will be symmetric because it is under the assumption that you are modeling Euclidean distances, unless otherwise you are bringing some other factor as a distance measure in a TSP. And the third important assumption is it satisfies triangle inequality. Triangle inequality means if you take 3 points ijk, dij plus djk is greater than or equal to dik. I think strictly greater than is triangle inequality. Okay, you will have this. Comes from the fact that in a triangle, sum of 2 sides is always greater than the third. Now, when you have this triangle inequality satisfied, it reflects itself in a different form. If you define a TSP, the normal definition of a TSP is a salesman starts from city 1 or any city, visits every city once and only once and comes back. This once and only once comes in because if your matrix satisfies triangle inequality, you can prove that the person will visit once and only once. If the, for example, you cannot have a solution where the salesman visits a city twice other than the starting city, of course, right. If you assume that city 1 is the starting city, the salesman will start from city 1, go back, complete the circuit and come back to 1. Every other city in a TSP, he or she is expected to visit only once, and that comes because of the triangle inequality. If you satisfy triangle inequality, any solution where the person visits more than once a city will always be inferior to a solution where the person visits once and only once. So, that once and only once comes because of the triangle inequality. Distance are positive, distance are more Euclidean, therefore they satisfy this. For example, if you have a distance matrix that does not satisfy triangle inequality, then it is always advantageous for you to go from I to k and k to j instead of I to j. So, the person will end up visiting a node more than once.
Then, because the distances are positive, it won't make sense to visit each other.
No, for example, if I want to go from say 1 to 5, if going through 4 is cheaper, I will always do that. Okay. and then for example from 5 to 7 I am going again, and if it turns out that going through 4 is cheaper, I will visit 4 twice. But when this condition is satisfied, I will never do that. So that is one thing which we will assume, unless otherwise stated, the matrix is square symmetric and satisfies triangular inequality, which implies that the person will visit every city once and only once. Now let us go back and start formulating. A person has to leave each city once. So sigma xij equal to 1, right? From every I he has to leave. So summed over j equal to 1 for every I. Person has to enter every city. So sigma xij summed over I equal to 1 for every j. Xij equal to 0 or 1, and minimize sigma dij xij. So let us assume that we have formulated the TSP this way. Okay. Is this answer correct, or is this formulation correct? It is not, simply because this is the formulation for the assignment problem. Okay, this is the formulation for the assignment problem. So there has to be something more which makes it a TSP. Now what is that? Now suppose we look at this matrix and we just apply this formulation saying that it is a TSP formulation, and let us also assume that we have not done this and we have used that the distance between any point and itself is 0. And now if you apply this formulation, what will you get? You will get all diagonal assignments x11 equal to 0, x22 equal to 0, z equal to 0. Why is it not a TSP? Because it is not a tour, right? It is not a tour. Now number 1 is, if you put zeros here, okay, then your travelling salesman problem for this formulation, which we will refine this formulation later, will give you all diagonal assignments. Now each of the diagonal assignments is a subtour. Now there are two things in a TSP. If I have a 5 by 5, if I have 1, 2, 3, say 5, 4, 1 is a tour, it is a feasible solution to the travelling salesman problem. For example, this will be reflected by x11 or x12 equal to x23 equal to x35 equal to x54 equals x41 equals 1. There will be 5 allocations and this will be the order of allocation, this as a tour. Suppose I have x12 equal to x25 equal to x34 equal to x43 equal to x51 equal to 1, then this, now let us try to get the tour or a subtour from it. You get 1 to 2, 2 to 5, 5 to 1, 3, 4, 3. Now this is not a solution to the TSP, this is a subtour and there are 2 subtours. Now a solution to the TSP should not have subtours. So what we need to do is, we need to add what are called subtour elimination constraints into this, and if you are able to do that, then we get the solution or the formulation for a travelling salesman problem. So you need to add subtour elimination constraints. Now for a travelling salesman problem of length n or size n, then you can have subtours of length 1, 2, 3 up to n minus 1. So you need to eliminate all these kinds of subtours. Now 1, every subtour elimination constraint would involve a constraint, and you want to minimize constraints in any formulation. So what you do is, you put a dash here which is like a big M, so that you avoid subtours of length 1. Moment you start putting infinity here or dash here, then the xii will not become an allocation in a TSP. So indirectly you eliminate subtours of length 1 by forcing the diagonals to infinity. That is the reason why you put infinity in the diagonals. So you have eliminated subtours of length 1. subtour of length. Suppose I have a solution which is like this, x11 equal to 1, x25 equal to x52 equal to 1, x34 equal to x43 equal to 1. There are 3 subtours, 1 to 1 is a subtour, 2 to 5, 5 to 2 is a subtour, 3 to 4, 4 to 3. There are 3 subtours. This is a subtour of length 1, this is a subtour of length 2, subtour of length 2. There are 2 links, so there is of length 2. There is only one link, so it is subtour of length 1. So now by forcing the diagonal elements to infinity, you have eliminated subtours of length 1. Now you need to eliminate subtours of length 2, and that will be like this, xij plus xji less than or equal to 1 for all I and j. For example, if I put for I equal to 1, j equal to 2, okay, you can also put I not equal to j, so that you can reduce some more constraints. So if I look at I2, I am trying to say x12 plus x21 less than or equal to 1. What will happen? One of them will have to become 0. So if you have x12 is in the solution, x21 will not be in the solution. If both are not in the solution, it is still acceptable to you, that is why I have put a less than or equal to 1. It may turn out that both 1 2 or 2 1 may not be in the optimal solution, therefore you put a minus, you put a less than or equal to 1, or in general for a subtour of length k you put k minus 1. So this will take care. The only problem is there are too many constraints. There are NC2 or NC2 minus n. If you leave out that I not equal to j, you put NC2 minus n. That many constraints you will have to put here. So if you add all this NC2, you have now eliminated subtours of length 2. Now go back and look at subtours of length 3. So when I have to eliminate subtours of length 3, then I have to put xij plus xjk plus xki less than or equal to 2, which means I will have NC3 constraints, because ijk can be chosen in NC3 ways. I have another NC3 set of constraints, and I will have another NC4 set of constraints. So the number of constraints becomes exceedingly large. But let us try to do something else. Now let us go back and look at this 3 constraint again. Now I have a TSP with 5 cities. Let us assume I have a subtour of length 3. If I have a subtour of length 3, the remaining 2 cities which are not included in my subtour can either form a 2 city subtour or 2 1 city subtours. It cannot form anything else. Therefore, if I eliminate all 1 city subtours and 2 city subtours, I am automatically eliminating all 3 city subtours. Is that clear? I repeat again, if I have a 3 city subtour in a 5 city TSP, then the remaining 2 cities can become either a single subtour of length 2 or 2 subtours of length 1 each. No other possibility exists. Therefore, if I eliminate all 1 city subtours and all 2 city subtours, I automatically eliminate all 3 city subtours, which I have already done. So I do not have to put this NC3. Similarly, if I have a 4 city subtour, there is only one remaining, and that has to be a 1 city subtour. I have already eliminated 1 city subtours, so I do not have to do the NC4. So in general, if I have an n city travelling salesman problem where n is odd, it is enough if I do till n minus 1 by 2. I do not have to do anything beyond. And if n is even, I will do up to n by 2. So when I have a 6 city TSP, I have to necessarily also eliminate the 3 city subtour, because a 3 can result in another 3, it can also result in another 3. So you do it up to n by 2 when n is even, and n minus 1 by 2 when n is odd. So you will have NC2 plus NC3 plus dash dash NC n minus 1 by 2 constraints if n is odd, in addition to these 2n, and NC1 plus NC2 up to NC n by 2 when n is even in addition to these two. So, you will realize that the number of constraints itself is exponential, because NC n minus 2, NC n by 2 or n minus 1 by 2 is exponential. So, number of constraints itself is exponential, but much later in the course when we look at TSP, we will at least see that this NC1 up to NC n minus 2, which is an exponential number, can be replaced by a set of n constraints or n square constraints. We will see that little formulation much later. Okay, but right now the understanding will be there will be a whole set of subtour elimination constraints which we have to make, and much later we will look at that formulation where we will have n square or NC2 or whatever number like that, NC2 constraints which is capable of modeling the entire thing. That will be a more efficient formulation of the TSP. So, the understanding here is to add the subtour elimination constraint, also the understanding that if you do it systematically, you can stop up to n minus 1 by 2 when n is odd and n by 2 when n is even. We will look at another formulation now. We look at a job shop scheduling problem. Let us say there are 3 jobs, there are 3 machines. So, you call the jobs A, B and C, you call the 3 machines M1, M2, M3. Now, let us say job A will have M1, M2, M3, this will be the root. Job B will have M2, M1, and say job C will have M3 and then M2. The associated processing time will be P I j, where I equal to 1 to 3 represents job, j equal to 1 to 3 represents machine. For example, this will need P11, P12, P13, P22, P21 and so on. This is called a job shop because the order of visit is different for different jobs. If for example, we say that all the jobs will first visit M1 and then M2 and then M3, then it becomes something called a flow shop, where all the jobs have the same order of visit. Now, if the route or order of visit depends or is different for different jobs, then it comes under a general job shop scheduling problem. Now, all the jobs are available at time equal to 0, these things have to be processed, and we want to now we will, when we start processing, each job will be completing at a certain time. For example, this, let us say all these 3 will be over if they are over by a certain time, say A1, and this is A2 and this is A3, or you call it some capital C1, capital C2, capital C3. What I want to minimize is called the make span, which is the time at which all the jobs are over. It is something like all the 3 jobs are to be done for the same customer. So, when all the 3 jobs are finished, I can pack them and send it to the customer. So, I want to send it to the customer at the earliest, and this is what I want to minimize. Now, I want to find out how I schedule these jobs in the system such that I minimize this. Yeah. C is the time at which this is over, C is the time at which this is over, C is the time, this is not given to you. C1, C2, C3 are not known. Okay, C1, C2, C3 will have to be found. The objective is to try and minimize the make span, which is the time at which all the jobs are ready and over. That is the objective. Now, let us formulate this problem. Let Tij be the starting time of job I on machine J. Now, my machine A, or I take the machine, I take for example job A. Okay. Now, for this certain things are very clear. T12 from 1 it goes to 2. So, T12 is the start time of job A on machine 2. So, T12 has to be greater than or equal to T11 plus P11, because job A first visits machine 1 and only then it has to visit machine 2, which means it should have completed its work in machine 1. And so, if Tij is the start time on machine 1 for job 1, then T11 plus P11 is the time it is over, and it can go to machine 2 only after this is over. This is a very straightforward constraint. Similarly, T13 is greater than or equal to T12 plus P12 is again a very straightforward constraint. As far as this job is concerned, T22 is greater than or equal, or sorry, T21 is greater than or equal to T22 plus P22. That is the only thing I have. And as far as this is concerned, T32 is greater than or equal to T33 plus P33. Please remember that this implies, for example, I can finish my stuff with M1. Any machine can process only one job at a time, that is an assumption. So, I may have to wait to get this M2. My start time T12 need not be immediately after this is over. This could be over, it could be waiting for machine 2, machine 2 may be busy doing something else, it waits, and once the machine 2 is free, it can go. That which means T12 is greater than or equal to T11 plus P11. So, these are simple constraints which are easy to model. The difficulty comes here. If I take machine M1, then machine M1 now has job A and job B going into machine M1. I do not know which one is going to go first, right? I do not know which one is going to go first. I have to decide such that it is advantageous to me. So, what I will do is, if I take a machine M1, either job A can go first and then job B can go, or job B will go first and then job A can go. So, you get into an either or situation. So, if you take M1, if job A goes first and then job B goes, then it means that T21 job B going into machine 1 will have to be greater than or equal to T11 plus P11, or T11 is greater than or equal to T21 plus P21. So, you have an either or constraint that comes in, which we have not modeled yet in our linear programming. We always know how to model fixed rigid constraints, but not an either or constraint. Now, similarly, if you take M3, it is either A and C. So, this is for M1. Now, for M3 you will get a similar either or constraint, which will be like this. So, M3 has A and C. So, you will have either T13 is greater than or equal to T33 plus P33, or T33 is greater than or equal to T13 plus P13. Because if you take M3, A and C, so jobs 1 and 3 So, starting time of job 1 on machine 3 should be after the completion time of machine 3, completion time of job 3 on machine 3, which is T13 is greater than or equal to T33 plus P33 or the other way.
So why can't you just write that T21 plus T11 greater than or equal to sum of the two answers?
Why can't I write?
Combine with one constraint, T21 plus T11 greater than or equal to T11 plus T21 plus T11.
Only one of them is valid. See, only when both are valid you can do the addition, etc. So, only one of them will eventually be valid. We will see how we model that. If you take machine 2, you get into a much more different situation, because M2 is handling all the 3 jobs. So, you have to write 3 sets of either or. For example, if you take the pair AB, then either A is ahead of B or B is ahead of A. If you take the pair BC, then B is ahead of C or C is ahead of A, and if you take the pair AC, either A is ahead of C or C is ahead of A. So, you will have 3 pairs of either or constraints. Since you are doing it first time, I will write down all the 3 pairs. So, you will, for AB you will have T12 is greater than or equal to T22 plus P22, or T22 is greater than or equal to T12 plus P12. This is for AB. Now, for BC, T22 is greater than or equal to T32 plus P32, and T32 is greater than or equal to T22 plus P22. This is one pair, and for 1,3 you will have T12 is greater than or equal to T32 plus P32, or T32 is greater than or equal to T12 plus P12. You have another set. So, in general, if all the jobs go through all the machines, then you will have mn pairs of constraints. Okay? Right. How do you model this? Now, this is where the integer programming comes in. We will just look at one of these, we can similarly model the rest of them. If you take one pair, what you first have to do is to write this in this form. So, if we take the first constraint, this is written as T11 plus P11 minus T21 less than or equal to 0, T21 plus P21 minus T11 less than or equal to 0. First thing you have to do is to write them as less than or equal to 0, and then you write this as T11 plus P11 minus T21 less than or equal to m delta 1, and T21 plus P21 minus T11 is less than or equal to m into 1 minus delta 1. I mean, initially let us call it only delta, let us not give any subscript to that delta, later we will do that. So, this will become m delta and m into 1 minus delta, where m is the well known m, large, positive and tends to infinity, the big M, and delta is the 0 1 variable. Now, what will happen? If this constraint is binding, that is, if it is advantageous for you to start 2 after you complete 1 in your final solution, if this constraint is binding, then this is the one that is binding, this is the one that is binding. So, your delta will take a value 0, and if this is binding, delta will take a value 0, implies this is redundant, 1 minus delta is 1, so it is a redundant constraint, less than or equal to m is a redundant constraint. If on the other hand the other one is advantageous to you, then delta will take a value 1 to make this binding and make this redundant. So, for every pair you will introduce a delta. Every either or constraint will have, every either or situation will have 2 constraints and a delta which is a 0 1 variable. So, you will have to introduce as many deltas as the number of pairs that you have. So, to make this delta, to give an identity to this delta, you can call this delta as say delta 1 to 1, because this represents jobs 1 and 2 on machine 1, right. For example, this constraint was written for machine 1 for jobs 1 and 2. So, you can call this as delta 1 to 1, this will be delta 1 to 1, delta 1 to 1 as a 0 1 variable. Similarly, you can name every one of these deltas. This will become in this case 1 3 3, and this will have the 1 2 2, 2 3 2, 1 3 2. For every pair you will have a delta. And then suppose I also say that if I for some reason or the other, if I put a limit on the completion time of each one, I say that job A has to be over by a certain due date, which is called DA, each has a due date or something like that, then that is a very simple constraint. Completion time of job A is nothing but T13 plus P13 should be less than or equal to D1. Now I have to minimize the make span. So I have the 3 completion times. For this the completion time will be T13 plus P13, this will be T21 plus P21, this will be T32 plus P32. These are the completion times of the 3 jobs A, B, C respectively. Now what do I want to do? I want to minimize the make span, which means I am minimizing the maximum of the 3 numbers. So I end up writing minimize some V, and V is the maximum of all of them. So what will happen? V is greater than or equal to T13 plus P13, V is greater than or equal to T21 plus P21, and V greater than or equal to T32 plus P32. You do not have to necessarily restrict your T's to integers or P's to integers, depends on the whole thing. It is likely that if the processing times are integers, then all the T's will also be integers and so on. So right now you do not have to worry about any of them, you will just say Tij V greater than or equal to 0, delta Ijk equal to 0 1. So this is a formulation for the job shop scheduling problem. Okay. Right. Yes. What is D1? D1, I hope there is no terminology confusion. D1 is called the due date for each job. Due date is something like a due time before which you have to complete the job. So if something like a D1 is given to you, then you will add a constraint saying completion time of job 1 should be before the D1, and completion time of job 1 is start time on machine 3 plus processing time on machine 3. So this will be a due date related constraint. Okay. If you want another thing, if I do not want to minimize this make span, instead I say that I give you a due date for each one of them, D1, D2 and D3. I am not going to force you to say that you have to complete before D1 or D2 or D3. I am going to say I want you to minimize the delay. I want you to minimize the total delay. Okay? That is a very reasonable objective. In that case, you assume that these 3 jobs actually go to 3 different customers, and each job has a certain due date given by the customer. Ideally, you would like to meet that due date. If you are not able to meet the due date, you would at least like to minimize the total delay that is there from your point of view. Then what will be this constraint will not be there. You are not going to be forced to complete within the due date. Then you need to look at one thing. Now we have these 3 different completion times. and you have associated due times with each one. We call them D1, D2 and D3, they are already written here. Now, the delay in scheduling sequencing terminology is called by different terms. Now, if this completion time is before the due date, then this job is called early. It is early, it is completed early. If this is after the due date, say, then the job is called, it is called tardy. So, a job can either be early or tardy. The term late is a very generic term. Lateness is the difference between the due date and the completion time. If the lateness is negative, which means the job is completed early. If the lateness is positive, then the job is behind, then it is called tardy. Now, what do you want to minimize? Right now you do not want to minimize the earliness, you are interested only in minimizing the tardiness. So, what you have to do is define a tardiness for each one of these. What will be your tardiness? Tardiness will be, say, D1 minus T13 plus P13 or minus D1, this will be your tardiness. This is the completion, this is the due date, correct? And if this difference is positive, then it is tardiness. If this difference is negative, then it is, what is the tardiness? 0. So, the actual tardiness is maximum of 0 comma T13 plus P13 minus D1, this is the tardiness, correct? If the job is early, this is negative, then your tardiness is 0. So, what you have to do now is you have to define a U1 greater than or equal to 0, U1 greater than or equal to T13 plus P13 minus D1. U1 greater than or equal to 0 is anyway a non-negativity constraint. So, you do not have to explicitly state this into the formulation as a constraint. So, you will just define this, and you will define a similar U2 is greater than or equal to T21 plus P21 minus D2, and your U3 will be greater than or equal to T32 plus P32 minus D3. You will also have U1 greater than or equal to 0, U2 greater than or equal to 0, U3 greater than or equal to 0. Now, your objective function will be to minimize U1 plus U2 plus U3, you will get this. So, depending on the objective function, the formulation will become different. If you want to minimize not only the sum of tardiness, but you also want to minimize the sum of earliness as well as tardiness, then you will end up doing minimize sigma modulus, say something, some Tij plus Pij minus Di. There are certain situations where even earliness is not desirable. What will happen is, if you finish a job early, you would like to send it to your customer. Customer may not want to receive it. He will say that I have put my schedule in such a way that this item is going to go to production only tomorrow. So, it is enough if you send me tomorrow or tomorrow morning, do not send it today morning or 2 days earlier. I do not want to hold that inventory in my possession, and those are issues related with operations. Okay. So, there are situations, tardiness is much more undesirable than earliness, but there are problems where this only we are interested in modeling. So, you will get something like this. Difficulty again will be, you have to write this explicitly, because this can be positive or negative, and then you have to handle it accordingly. It is not, the modulus is not directly a linear thing. So, again you have to convert this modulus into another linear thing. So, these are the issues. The understanding particularly from the job scheduling is understanding of this either or, and that is the most important thing. The either or constraint will keep repeating again and again in every integer programming formulation, particularly when you are looking at processes and manufacturing related issues, where a job or a processor can handle only one job at a time. moment it can handle multiple jobs, you do not have to worry so much, but then if it can handle a maximum of k jobs, then you have to put another constraint, y1 plus y2 plus yn less than or equal to k, and y will be a 0 1. So, all these are issues in formulating examples. There are still one or two more examples that we will look at in the next lecture, and we will